Let's take a look at a few more examples, but this time with the vectors in three-dimensional space. So here we want to describe the span of two vectors, but both vectors live in three-dimensional space. So what are we going to get here? Well, the trick here is we need to check to see if the vectors are, if I can express one vector as a linear combination of the others. Okay, in this case, can I describe maybe this vector as a linear combination of this vector? So in this case, that'd be a multiple. And with a little thought, we realize we can, right? 4, 6, negative 2 is going to be equal to negative 2 times negative 2, negative 3, 1. So anything that this vector is describing in the span, its contribution to the linear combination, can be taken over by this, right? If vector v is equal to some constant times 4, 6, negative 2 plus some other constant times negative 2, negative 3, 1, and any vector in the span has to be described this way, right? That's what it means to be in the span. There's some vector a1 or some scalar a1, some scalar a2, so that we could describe a vector in the span this way. But four, 6, negative 2 is just negative 2 times negative 2, negative 3, 1. And if I factor out the common vector, I get negative 2a1 plus a2 times negative 2, negative 3, 1. Which means any vector in the span can be expressed as some scalar times just the one vector, negative 2, negative 3, 1. Okay, so in a way, we really don't need both of these vectors to describe the span. This one vector does the job on its own just fine. Okay, now if we just have one vector, then what do we have? What's the graph look like? So we're in 3 dimensions. We have some vector in 2-dimensional space. What, negative 2, negative 3, 1, somewhere over here maybe. And we're just looking at different scalars of this vector. We're just scaling this vector. We're looking at different linear combinations. We just scale one vector. By multiplying it by a positive scalar or a negative scalar, we just get a line. So this is going to describe a line in R3. So the vectors span a line in 3-dimensional space. Okay? Take a look at another one. Here, again, we want to describe the span of two 3-dimensional vectors. This one's 1, 0, 2, the other one's 0, 1, 3. So can we express one of these vectors as a linear combination of the other one, or vice versa? Well, in this case, no. And it's pretty easy to see if you just think about the zeros. No matter what I multiply this vector by, I can't multiply 1 by some non-zero value and get 0 here. Okay? I can't do that. And I can't multiply anything by 0 here and get 1 here. Just can't happen. And vice versa. I can't multiply a 0 to get a 1. And if k isn't 0, I can't multiply 1 to get 0. So those are two reasons why it's not going to work. These are not redundant vectors. I can't express one of these vectors as a linear combination of the other. Okay? So if we have two vectors that are, in a sense, independent from one another in three-dimensional space, and I'll just draw them very roughly here. 1, 0, 2 might be kind of like that in the XZ plane. 0, 1, 3 would be kind of like that in the YZ plane. Okay, so we have two vectors. I could go anywhere that those two vectors are pointing. Since they're independent, I can go anywhere in, let's see, actually it'd be more like, there's a plane that they go through. Okay, and they could reach anywhere in that plane. So these two vectors, they span a plane in three-dimensional space. So hopefully you're starting to see the pattern. You need, back here, we had two vectors, but they weren't independent, right? One of these vectors could be described as a linear combination of the other vector. It wasn't really adding anything. So really, I only had one useful vector with new information, one independent vector that was independent from the other. That meant I had a one-dimensional object, a line. Okay? These two vectors, in a sense, are independent from each other. I can't express one as a linear combination of the other. They both are contributing information here. And so when I have two independent vectors, two pieces of independent information, I get a two-dimensional object, a plane. Okay, let's take a look at this one. Can I express one of these vectors as a linear combination of the others? Okay, this one's a little trickier, but the answer is no. So for example, this one, can I express it as a linear combination? Well, in order to do that, I need what? To multiply this by negative 1/3 to get a 1 there. Okay. And then add to it, well, it'd have to be a 0 here, right? So I could get a 0 there and a 0 there. But then I'd have a 1 here, or a negative 1/3 down there. So it doesn't work. And the same is true for all the other ways that you can think about this. Okay. We think about this as a linear combination of the other two vectors. Is it possible? Can I find scalars a1 and a2 to make this work? Okay. So I gave you a brief explanation, but let's talk about it a little further. This top number has to be 0. Okay. So that means I need a1 times 2 plus a2 times 0 to equal 0. But a2 times 0 already is 0, so that's covered. a1 times 2 would have to be 0, so a1 has to be 0. That has to happen to make the top entries work. 0 equals 0 times 2 plus something times 0. Okay? Let's go to the next line. For 1, I need a1 times 0 and a2 times negative 3. Well, in order to make that work, since this is 0, I need a2 times negative 3 to be 1. And so a2 would have to be negative 1/3. Okay? But then the third line doesn't work. So I get 0, and then this would be, since a1 is 0, I get 0 equals 0 plus, and then a2 is negative 1/3, so 0 plus negative 1/3. So this last line would be 0 equals negative 1/3, and that doesn't make sense. Okay, so this is impossible. Okay, and same thing if we look at it in any other linear combination. Expressing 2, 0, 3 as a linear combination of the other two vectors. Is impossible. And all you have to do is look at the first line. There's no way I could get a 2 by adding zeros together. A1 times 0 plus A2 times 0 is guaranteed to be 0. Right? So that's impossible. What about the last vector? Can I express that as a linear combination of the other two? And I can't for the same reasons. A1 would have to be 0. A2 would have to be negative 3. But then I get 0 plus 0 equals 1. That doesn't make sense. So that's also impossible. Which means all of these are independent. There's no redundancy. Okay? They all are giving useful information here. Okay? So if I have 3 vectors that are all giving useful information, what does that look like? So 2 of those vectors, if I look at just the span of 2 of those vectors, I get a plane. So 0, 1, 0 is on the y-axis. And then what was it? 2, 0, 3 in the xz plane. Okay, and so I get a plane and then my last vector allows me to move away from the plane. So 0, negative 3, 1. It allows me to kind of move. It's kind of hard to draw. I'll draw it this way. It allows me to move away from the plane, okay, to the rest of space. So with all 3 of those vectors together, I will be able to reach anywhere in 3-dimensional space. So the pattern continues. We have 3 vectors that are independent that all contribute something useful to the span, new information in the span. So when we think about all 3 vectors, it spans 3-dimensional space, the whole of 3-dimensional space. Okay, one last example here. Here we have the span of 3 3-dimensional vectors again, but this time we do have redundancy, right? Because our last vector, 1, 0, 1, is just equal to 1 times our first vector, 1, 0, 0, plus 1 times our second vector, 0, 0, 1. Okay, so these 2 vectors on their own give us all the information we need. This last vector doesn't tell us anything new about the span. Doesn't give us any additional useful information or useful direction that we could be in. Anything we could do with this, we can do with these 2 already. Okay, if vector v is in the span of the 3 vectors, then I could replace that last vector, 1, 0, 1, with 1 times 1, 0, 0 plus 1 times 0, 0, 1. I'm just going to take this, plug it in for that last vector. So I get 1 times 1, 0, 0 plus 1 times 0, 0, 1. And if I combine like vectors, I have a1 plus a3 times 1, so that's a3 of the same vector. So I get a1 plus a3 times vector 1, 0, 0. Plus, and then a2 times 0, 0, 1 plus a3 times vector 0, 0, 1. So I get a2 plus a3 times vector 0, 0, 1. Which means that any vector that is a linear combination of the 3 vectors in my spanning set, the 3 vectors that are our spanning set here, any vector in the span is also in the span of just the 2 vectors. I just need those 2 vectors to span the set. So that third vector is redundant. And we know that 2 vectors, 2 independent vectors in 3-dimensional space are going to form a plane, right? They span a plane. So the vectors span a plane in R3.